Okay, welcome back. We are now going to conclude the proof of Hamilton for the convergence of Huisken-Ricci flow on two surfaces of positive scalar curvature. Let's just recapitulate how far we got. We had, on the other hand, on one hand, proof that the solution exists for all time. We have just proven a Harnack inequality on the scalar curvature, and now we have proven an estimate which is somehow better than the scaling. We have shown that the integral of r log r is bounded. Now this is integral of r is of course fixed by the Gauss-Bonnet integral, so we have sort of a tiny little indication that and a first upper bound, the first estimate that that some quantity involving r is bounded above, which is better than the scale-free term d mu times r. So we are just a little bit better, just by logarithm better than what we knew before. Now the idea is to exploit this term with the help of the Harnack inequality and say that if somewhere the curvature would be huge, then because of the Harnack inequality it would be big in a whole neighborhood. But if it is big in a whole neighborhood, then this integral should contribute a big number, because the d mu times r, because it's scaling invariant, should always contribute the same amount in a small neighborhood, so the log r should win and contradict the fact that this integral is bounded. Okay? So to do this technically, you just have to be a little bit careful about these scales and the region where we apply the Harnack inequality. So consider, so the theorem says there is a bound C2 depending only on the initial metric, such that the scalar curvature is less than C2 on sigma 2 cross 0 infinity. So the proof proceeds like this. Suppose that at time t1, R max is attained at some point p1, and then choose T2 not too far away. So choose T2 such that T2 minus T1, right? So now we wait a little bit. At T2 minus T1 is say 1 over 2 times R max at time T1. Notice that this scales the right way. Scalar curvature scales like 1 over distance squared, so this scales like time, so this is just the right scaling. And then we look at the evolution equation of this scalar curvature. So note that ddt of r was Laplacian r plus r times r minus little r. So this means in particular that this is less than Laplacian of r plus r squared, which means in particular that ddt of r max is less than the maximum. The Laplacian is less than 0, so this is less than r max squared. So in the sense of lim sup of difference quotients. So this means this cannot grow too much in this time interval from t1 to t2. So this must mean that the r max at times t2 is less than twice than r max at time t1. Okay? So we have chosen our time interval sufficiently short that r max at this later moment is comparable to the curvature at time t1. Now, since on the other hand ddt of gij is equal to r minus capital R times gij, and now the curvature is now comparable on the small interval between t1 and t2, we know that the distances between 2 points on this small interval cannot change by more than a constant factor. So we know that the distance ratio of the distance between P1, P2 at T1 to the distance between P1 and P2 at T2 between 2 points can be at most by a certain constant, say C2, which is bounded. Because the speed here is comparable to the inverse of the time interval, so this cannot deteriorate in this short time. So we know that the distances are comparable. So if we plug this into the Harnack inequality, this gives us control on the delta, which was the infimum of the integral of gamma dot square for any curve between P1 and P2. So then note that the delta, which was the infimum of our possible curves between P1 and P2 at two events, P1 T1 and P2 T1, this means that this can be estimated from above by the distance at the later time squared divided by T2 minus T1. And so if our distance from P1 at the later time is not bigger than the square root of T2 minus T1, then this number here is bounded. And also if T1 and T2 are comparable, then you can make this thing bound. So this implies that in the ball of radius rho equal to some delta times T2 minus T1 to the minus 1/2, which is equal to delta times T2 times to the plus 1/2, which is delta times some constant times R max at T1 to the minus 1/2 around P1. We have that by the Harnack inequality that R P2 at time T2 at the later time is bigger than some positive constant times, and this is also bounded, times R P1 T1, but R T1 T1 is R max at times T1. For some C bigger than 0, for little c's bigger than 0. So we have this little ball where at the slightly larger time we have a uniform lower bound, just we have comparison. So the curvature is just as big up to a constant as at this maximum at the earlier time. Now, on the other hand, we are in the positive curvature case. Therefore, remember, in the positive curvature case, there was this estimate of below of the injectivity radius in terms of the curvature. So also, the injectivity radius at P1 at P1 at time T2, because we have this bound on the curvature, is bounded below by some number delta tilde times R max at T1 to the minus 1/2, because we have this lower bound on the scalar curvature. Radius C Klingenberg's lemma. Okay, so we have a lower bound on the injectivity radius. Therefore, we know that the measure inside this ball of this radius must be comparable to R max to the minus 1. Therefore, the measure or integral 1 mu over this ball of radius rho tilde around P1 at time T2 and measured with respect to the measure at time T2 must be bigger than some little delta tilde times R max to the minus 1 times at time T1. But this means, since on the other hand, I have on this ball this scalar curvature bigger than the R max as well, I get that the integral of R log R d mu over sigma 2 at time T2 can be bounded from below by this integral over this rho tilde at P1 at times T2 and R log R And this whole thing remains. So from the d mu, I get an r max to the -1, but from here I get an r max to the +1. So I'm left over with some small number times the log of r. And the right, and this would this gives us, and since this is uniformly bounded, this implies that R must be bounded. Must be bounded. With R max at time t1. So R2 max must be bounded. But T1 was arbitrary. This is QD since T1 was arbitrary. Okay, this gives us the upper bound on the scalar curvature. But now, once we have the upper bound on the scalar curvature, we go back once more to the Harnack inequality. Now, if we have an upper bound on the scalar curvature, right, so the upper bound on the scalar curvature and the right, then I claim that the Harnack inequality gives us a lower bound on the scalar curvature as well. Why is that? Let me just check. Right, so since the scalar curvature is positive and bounded above, so R is now less than some constant C2 less than infinity. This means, and since we are in the positive case, so we have a lower bound on the injectivity radius everywhere. So every little ball contains a certain amount of volume. Now, if the diameter was arbitrarily large, I could select a string of balls going to infinity, all having a fixed little radius bounded below by the injectivity radius, and each one of these balls would contribute a certain amount to the volume. That contradicts the fact that we fixed the volume. So, since the volume is bounded, and the injectivity radius is everywhere bounded below by some constant delta times R to the -1/2, which we've just seen, and this is, since R is bounded above, this is bounded below by some delta hat bigger than 0, it must mean that the diameter is bounded. Remember that this was our enemy. Our enemy was that maybe the volume is bounded, but we have sort of the situation that the volume is bounded and the scalar curvature is huge here, it's close to 0 here. So this no longer can happen. The diameter is bounded, we cannot have this deterioration. But if the diameter is bounded, then since this here is comparable to the diameter divided by the right time interval, we can make this constant fixed now. And the maximum, of course, is always bounded below is always bigger than the average, which is bounded below by the Gauss-Bonnet integral, we now get a lower bound on the scalar curvature in terms of the maximum. So, so now the diameter is bounded above, then the Harnack inequality implies that the scalar curvature is bounded below some sigma positive everywhere on the surface. So now we have a lower bound on the scalar curvature, positive lower bound, and we have a upper bound, uniform, with scalar curvature completely under control. What remains to show is that the thing converges. And here comes, that's what makes the two-dimensional case so interesting. We have all seen all these techniques. We have introduced the potential, we have introduced the Harnack inequality, we had this entropy estimate integral of R log R, and now we've finally gotten an estimate on the scalar curvature above and below. Turns out this is still not enough. We still have to prove something to show convergence. And in fact, we have to do something non-trivial to show convergence. And the idea is the following, namely to go back again to the potential. Actually, I should first make a remark. Why we still have to do something. There still has to be a non-trivial argument. Everything we've done so far is still valid on a so-called orbifold. An orbifold is something which is a manifold everywhere, but has maybe one point which has a chart which is not a usual chart into Euclidean space, but a chart into Euclidean space divided by some finite group, say finite group of rotations in the two-dimensional case. So there's one point P in sigma 2 has a chart which looks like a ball, a disk, like a usual disk, but divided by a finite group of isometry. So it has something like a cone point where rather than, but it's completely smooth. Everything's smooth, differentiable. It's just that the chart looks like this. And you should think of such a, if you try to visualize it, you should think of something like a smooth manifold, which somewhere here has sort of this cone point, where rather going around 2 pi, you go around 2 pi divided by q. But the curvature is still perfectly bounded. So everything we've done, we could have done, all the analysis we could have done on this thing, including the Harnack inequality and everything, except some argument, there would be some harder argument of the injectivity radius at this point and so, but in principle we could get up to here. And it turns out, on this thing, the Ricci flow does not necessarily converge to a round metric, but there are solutions which never change their shape. There are non-trivial solitons on this thing. There exist non-trivial soliton solutions. In other words, that only move by diffeomorphism. And on these things, we don't have the scalar curvature identically equal to the average. So we have to still use an argument that does not work on orbifolds. Okay? But this also indicates to some extent that maybe we have to use an argument that has to do with solitons. And it turns out that this argument can be set up using the potential that we were using before. So we call that there exists f with Laplacian of f equals r minus r, and integral of f dmu equals 0, and we had an evolution equation for f. ddt of f was something like Laplacian of f plus r times f, and there was plus or minus some b, and the b was something like the average of gradient f squared dmu over integral dmu. And we had this potential function, and this potential function we had been using in order to prove that there is a long-time solution of the flow. And this was, let me just check here that I wrote down the right evolution equation. Yes, it's exactly right. This is the right evolution equation, and we use this to prove that there's a long-time solution of the flow. Now, it turns out we should try to control the metric looking at, we want the Laplacian of f, the trace of the second derivatives, to go down to 0. So it turns out we should look at the trace-free part of the second derivatives. So the idea is to consider the tensor Mij, which is just the Hessian of this potential minus 1/2 the trace, which is Laplacian of f times Gij. So this tensor is symmetric and it is trace-free. Now, because it's interesting, we should compute its evolution equation. And now I'm getting tired, so I'm not going to do it. I leave it as an exercise. The result is this remarkable thing. If you compute the evolution equation and then you take the square, be careful, because the square, Mij squared, is of course formed with the help of the metric. So you have to differentiate also the two metric terms when you compute this evolution equation. Be careful when exchanging the time derivative with the Hessian, say you have to do the derivative of the Christoffel symbols again. But it's straightforward, a straightforward computation, and you get the ddt of the square of Mij is equal to the Laplacian, what you expect, and then you get the Bochner term, and then you get magically minus r times Mij squared. This is for the rescaled equation. But for the rescaled equation, we had a lower bound on capital R. So this is just a computation, which I leave to you. And now we exploit it with the maximum principle. This is a negative term, this is a Laplacian, this is a scalar quantity. We exploit the fact that R, in our last theorem, we have proven that R is bigger than some number sigma bigger than 0. So we get, by the maximum principle, that this tensor Mij squared satisfies that this is bounded by the maximum of Mij squared at time 0 on the initial surface times e to the minus sigma t. So it goes down exponentially fast. Finally, we found something which goes down to 0. Now, the usual induction steps we can also then show by induction that all higher derivatives converge exponentially fast. So gradient m, Mij, all higher derivatives also decay with slightly worse constants. So we get exponential decay of this thing in all norms towards 0. So this means if we now look at an evolution equation, where this is the speed of the metric, consider the equation dd, let's call it dd tau of g tilde ij of tau is equal to 2 times this Mij. Of metric g of tau. Then, now what is this? 2 times Mij. Up there is Mij. This is 2 times di dj f. But from this one we get minus Laplacian of f. So this is r minus capital R times gij. So if we look at this particular evolution equation, let me drop the, let's just write t. If I look at this evolution equation, which is just my old rescaled Ricci flow, changed by a diffeomorphism in the gradient of f, then this flow, in other words, if I change my original Ricci flow by a tangential diffeomorphism term in direction of gradient f. So this was my very first lecture on Ricci flow, lecture 1. We saw that this thing here is equivalent to ddt gij equals r minus r times gij up to tangential diffeos in direction of x equals gradient f. Right, so this is okay. It's equivalent up to the old flow. So this flow that's been changed with the help of gradient f, this flow converges exponentially. So now, if we can show that what is the limit? Why? It converges to what? It converges to something, of course, where Mij is 0. And Mij being 0, of course, means we are on a Ricci solenoid. Yeah, so maybe I should call it G tilde. So, so get exponential convergence to some smooth, because we have everything converging, some smooth G infinity, satisfying that r minus little r gij infinity is equal to twice the Hessian of F. And this is a Ricci soliton. And in this remark I just made, on these orbifolds there are Ricci solitons. On these orbifolds there are Ricci solitons. So in these orbifold cases we get something non-trivial. The point is that it is possible to prove that if we are on a closed manifold which is smooth, then there is no such soliton. So so the last proposition, and this finishes the proof of the main theorem. There is no non-trivial Ricci soliton on S2. In other words, the flow converges to the round network. This implies F is 0, and the metric and G of T converges itself without making this change, right? So F is 0, and therefore this term is not there, and therefore then this flow converges to a metric of constant Gauss curvature. Okay. Now this has this proof that I'm now presenting has one drawback. Namely, I'm using the fact that I'm on S2. I'm already using Gauss-Bonnet saying a positive scalar curvature. I know that I'm on S2. So I'm using the fact in this proof that I'm on S2 in order to show that the flow converges. If you work a bit harder, then you can prove this proposition in the case of just using positive curvature without knowing S2. But then the proof gets nasty, or you have to use complex notation, which I don't want to introduce. Okay, so I'm just presenting this argument, and it works like this. Consider consider the fact that we have S2 since G, so we can write G ij at T as some e to the u of times Gij at time 0. We have, at the very beginning, when I talked about the two-dimensional case, we said we stay in the same conformal class, so I can write the conformal factor as e to the u, and then we get an evolution equation for u, which was something like e to the minus u. Let me check. We get e to the minus u times Laplace u e to the u. Let me check. E to the minus u times Laplace u minus r. I think was the evolution equation for Ricci flow, and then the consider the energy that comes from the Yamabe problem where you such that the equation of constant scalar curvature becomes the Euler-Lagrange equation of this energy. So here you have R times U d mu, and you take this with respect to the background metric, and this is the scalar curvature of the background metric, and this is the metric on your background. So you take this energy, it's a relative energy of the metric G with respect to the metric G0. You could also put some other background metric. And now you actually have to put a 2 in here. Now you use the evolution equation for U and compute what is ddt of E of U. So then the simple computation, ddt of this relative energy of the evolving surface with respect to the energy of the background metric, you get ddt of E of t turns out to be something very clean. It has to be something geometric. You can already see what's happening. You get 2 times di u times di of Laplace u. You do an integration by parts, and then you get this term squared, but the Laplacian just relates to the scalar curvature, so you end up with minus the integral of the scalar curvature at the time t, this is, squared d mu t over sigma 2. So you get this flow. Now, if we are, but this relative energy, of course, is completely independent of, and its change, completely independent of any tangential diffeomorphisms that we make. So, if we are on a Ricci soliton, if you have something satisfying this equation with some f, then this integral on the right hand side would be just some constant, some negative constant. And it would not change because we are moving on, we are sitting now on the soliton and we're solving this equation. A soliton is a solution of Ricci flow, a solution on which this integral never changes. But the equation is right. So on a soliton, integral r minus little r squared d mu is fixed, is a constant, independent of t. So we have only two possibilities. Either it's identically zero, and that means the only soliton is the soliton with constant curvature, that's the one that we want, or it's negative, and since we have a solution for all time, the energy this relative energy must go to minus infinity. So if r is not identically equal to little r, to its average, then E of t goes to minus infinity. And then there is a famous theorem by Onofre saying that on S2, the energy is bounded below. So, but Onofre, actually that's related to the Trudinger, the special Trudinger-Sobolev inequality on S2, which is of independent interest itself. So there is a sharp Sobolev inequality that says that this energy here in du squared, there's a Sobolev inequality for integral du squared on S2 that says that this energy is bounded from below. E is bounded below on S2. And this would be a contradiction. And therefore, we must have that this term is identically zero, which means that the scalar curvature on the soliton is constant, so the only soliton is the constant Gauss curvature metric, which just sits there and doesn't move. Right. And of course, in the example that I mentioned to you, this orbifold thing, on that thing, on the soliton, the energy actually does go to minus infinity, because somehow the surface concentrates more and more at this orbifold point. So this, at this very, very last step, we have used that we are on S2. Only then. Everything else remains the same, even on orbifolds. And in fact, there's a beautiful paper by Lanfang Wu many years back, where she proved the convergence to the solitons on orbifolds. So, but on the two-dimensional setting, this finishes the proof in the case of a positive Gauss curvature. And as I mentioned, you can give a different proof which rules out the orbifold type soliton on S2 in a different way, for example, by reducing it first to the rotational symmetric case, and then showing that in the rotational symmetric case, either you get a metric which has some singularity, which would be the orbifold point, and if it is smooth, then the only solution is the round sphere. But that's slightly more technical and not part of what I want to emphasize here. So it remains to make a comment about the case. The only remaining case that we have not covered now is the case of S2, if we have a metric which does not have positive scalar curvature everywhere. So that's one last remark. So the last remaining case we have S2 with a metric G0, but scalar curvature of G0 may have both signs. Okay, then the point is consider the evolution equation for R. You get dBTR, still have this equation, is equal to Laplace R plus R times R minus average. Now, this term here is always this term here looks like it wants to improve the metric, and in fact you can use the ODE. If there was just R squared, we know it goes up like 1 over T. But if we don't have the, let me just check just a second. If we don't have positive, if we do the rescaling and have the extra term with the little r, then it turns out that the ODE that corresponds to the right hand side, so we have dds of phi equals phi times phi minus a constant. Little r is a fixed constant. This has the solution S t, I should say, S of t is equal to little r times 1 minus r over s at time 0 times e to the rt and this whole bracket to the minus 1. Okay? So this says that as t gets if t tends to 0, then we just get just the original value of s of 0, right? And if, because it's in the denominator here, and yeah, I should call it phi of t. This is phi of 0. Right, so this slowly approaches zero, so then can carry out the whole proof with r minus phi of t instead of r. Since r by this maximum principle, r bigger than phi is preserved. So you, in particular, you then look at, for example, you get that the integral of log of r minus phi times r minus phi dmu is bounded by a constant less than infinity. And also the Harnack inequality can be applied to r minus phi. And then you just apply everything to r minus phi, and then the proof goes through. I think it's not you just have to make this observation that there is a solution of this ODE, that you can subtract it from r, and get something positive, and all the quantities make sense. And this was carried out in a paper by Ben Cha. Yeah. Okay, this completely completes the proof of the Ricci flow in the two-dimensional case, and I just want to remind you of the key things that we used. We used a potential which turned out not just to give us the long-time existence, it also allowed us to prove the convergence if we modified the flow by tangential diffeomorphism in the direction of the gradient of this potential, and only then we got exponential convergence. So this need to make the tangential adjustment before we get convergence to Ricci flow, this is a crucial new feature that we didn't have in the other cases of positive curvature. So here we have to make this tangential adjustment, which will recur when we look at the work of Perlman. And the second thing is we had to use a delicate integral estimate, just involving the log of r, in order to get the estimate, and it was absolutely crucial to have a Harnack inequality. So the Harnack inequality gave us the tool to compare curvature at the maximum and curvature nearby. The curvature cannot drop off too fast. If we had a gradient bound on the curvature right away, it would have been even better, but that was not available. There's a Harnack inequality, and the Harnack inequality was a crucial tool in order to exploit the integral on log r times r. And then we got the convergence to a soliton, and then we classified the soliton. Only soliton is the round sphere, and that completed the proof. And all these ideas of integral estimate of a logarithm and the Harnack inequality and the interaction with the diffeomorphisms are going to be crucial in studying Perelman's work. So in the next few lectures, I will introduce into the monotonicity formula of Perelman and how they can be used to get a lower bound on the injectivity radius and therefore a compactness theorem and allow some rescaling. Let's see how far we get. Thank you.